Hello everyone, this is Doug, and in this video we're going to start talking about some of the electrophilic aromatic substitution reactions, namely the halogenations. So by halogenations, right, we're just talking about putting a halogen on an aromatic ring. Again, we're going to focus mostly on benzene, but these reactions could work on other aromatic compounds. So chlorination, bromination, iodination are going to be our big three. We're not going to see any direct fluorinations, so you don't have to worry about that one. But like I was saying in a previous video, these reagents are very sort of self-contained to aromatic compounds. And what I mean by that is that chlorination, for example, normally if I wanted to put a chlorine on an alkene, right, just a regular CC double bond, I would just add Cl2. But that's not going to work that great for benzene. And so what we do is we add a catalyst to help it, right? So in this case, it's aluminum trichloride is the catalyst we can add. And I'm going to show you the mechanisms later, but I just want you to see the reagents now, right? So we started with just plain old benzene. We add Cl2 and AlCl3. We put on a chlorine. The side product here is that you form some HCl. But again, this is organic. I don't really care about things like HCl. So plus HCl. Now bromination is going to look kind of similar in that we're going to add Br2, but bromine by itself, I mean, it depends on the ring, but generally speaking, you're going to see Br2 also with the catalyst, often something like Br3, or you could see AlBr3, but either way, it's going to have some sort of catalyst also. And that's just going to help make the bromine more electrophilic so that you can do our electrophilic aromatic substitutions. And then again, you have HBr as a side product. Now, iodination is going to look a little bit different. For the iodination, we're not really going to add I2 directly. What we usually do is we add something like sodium iodide, and then we make the iodine in situ. We make it in the reaction vial, the reaction container, by oxidizing it with hydrogen peroxide. So by taking sodium iodide and hydrogen peroxide, we're able to make an iodine species that is able to be attacked by the bromine. And when you do this reaction, you see like the kind of brownish of iodine start to form as you do it. And like all the other ones, you end up making a little bit of HI afterwards too. So those are just kind of the sets of reagents. These are good reagents to know if you want to chlorinate, brominate, or iodinate a aromatic ring. These are the sets of reagents you're going to see. But I wanted to show you a little bit about this mechanism so that if I ask you, or just so that you can learn more about how these halogens get on and what we mean by making something a better electrophile or a super electrophile. So I picked bromination for this one. And I'll say this again at the end, but the chlorination mechanism is identical to this. You just basically switch out chlorine for bromine. I am not going to ask you about the iodination mechanism. It's still a little fuzzy and probably involves hypoiodite or something like that. But the bromine and the bromination and chlorination are real classic mechanisms. So what I'm going to show you first is the making of this super electrophile, right? So I've got Br2. Let me drop Br2 with all of its electrons. And in this case, I've got my iron catalyst, right? My iron tribromide, or my iron 3 bromide. And I'll do all these electrons. This is a mechanism. And the idea here is that if I take a look at this, right, I've got my bromines, which are partially negative, right? They're more electronegative than iron, so iron's getting pretty positive. And lo and behold, over here, my bromines, right, have so many electrons to give. They can give some electrons to this iron. This is not an inorganic class, but iron has some empty orbitals in the D shell that you can add electrons to. Let's not stress about this, but let's just acknowledge the fact that the iron can act as a Lewis acid and the Br2 can act as a Lewis base. And if we do that, what we see is that we're going to make these bromines even more electrophilic and even more reactive than they were not attached to the iron. So if I draw this out, So if I draw this out, now my Br2 has added to my FeBr3. Right, we have this adduct, we have this Lewis acid base pair. But when we do that, what we see is that now my iron is negative and this bromine became positive. And as you can imagine, right, bromine does not want to be positive. I'll say it doesn't want to be positive. right? If anything, it wants to take back electrons. Right, it's positively charged, and bromine is in the rightmost column. It's not super electronegative, but it's relatively electronegative. So what that means then is that this bromine over here on the end becomes very electrophilic. It becomes a very good, let me say, I'll say it becomes a great electrophile. Right, it becomes a great electrophile. And this is what's going to allow our benzene to attack it. So I'm just going to kind of draw this separately out so that we can see this all put together, and then I'll uncrowd all those notes. So the idea is that I have my bromine, I have my benzene. It sees this iron bromine adduct with all these lone pairs. That's negative, that's positive. And again, what this allows us to do is now it allows the benzene ring to attack this bromine. And like we were saying over here on the left, right, we said that this bromine in the middle here is positive. It doesn't want to be positive, it wants to take back electrons. It allows that bromine there in the middle to take back electrons, right? It gives that positive bromine electrons back. And that's going to allow us to, we have a positive, there's a bromine here now, and H is on that carbon also, but we've now made a bromine attached to an iron. So we have a FeBr4 minus, and then our bromine has added to our electrophilic aromatic, our ring. And that was the first step, right, of that electrophilic aromatic substitution mechanism that I mentioned in a previous video. And then I would draw all of the resonance structures. Should I draw them? I'll draw them. I'm trying to teach you guys to do this. So I draw the resonance structures. I'm just feeling lazy right now, that's all. But the resonance structures would look like this, right? Again, this should look a lot like what we saw in that previous video, where I can take these electrons, move them around again. Positives here, bromine, hydrogen, right? So all of these are the same molecule. The resonance contributors are the same molecule. And then we said that the last step of these electrophilic aromatic substitutions is that the H gets plucked off or leaves because of something. And now we've reestablished our aromaticity. The bromine is still on there, but now I have an H plus floating around, and then I still have my iron bromide species. Now, I don't really care about you showing me the mechanism of the iron thing, but that iron would then spit out one of those bromides so that it becomes FeBr3 again, and you have Br minus. And then that catalyst, that FeBr3, can go back and catalyze another one of these reactions. So it gets regenerated. And that's basically the mechanism, right? I know it kind of got laid on top of each other, but it's just the first step and the second step, right? You add the bromine, there's some resonance structures, and then you lose the hydrogen. You do an elimination, and so you get the brominated benzene. And that's really it. Like I was saying at the beginning of this slide, if this was the chlorination, it would be the exact same mechanism. The only difference is that you have chlorines here, and you'd have aluminum trichloride would be the thing. So you'd have your Cl2 attack an aluminum with 3 chlorines on it, but then all the rest of this would be identical, exactly the same. So you can look in your book and see that for yourself. Again, not going to ask you the iodination, don't sweat it. So now I'm not going to do a lot of examples of this because it's just 3 reactions, and it's just, do you know the reagents or not? I'll talk about the syntheses problems in a second here, but what you should be able to do at this point is just be like, oh, look, I see Cl2 and aluminum trichloride, so I'm just going to just put a chlorine somewhere on my aromatic ring. You know, later we'll talk about directors. Later when we know more about these reactions, we'll make them more complicated. But right now, you just throw the chlorine somewhere. Same thing with the second one. Oh, if I need to put an iodine on there, then I know that I need to add something like sodium iodide. and hydrogen peroxide, right? If I want to put an iodide on there, right? And I could have done bromine, but it's the same thing. Just learn those reagents. Those are the reagents that are going to help you do these halogenations. What this does for us, though, is it allows us to open up what we can do as far as synthesis problems go, right? So I have two right here. I recommend you pause, see if you can incorporate these into the synthesis reaction. I have to start with plain benzene, hint, hint. I think you know what your first steps are going to be, but then how do you turn those into your final product? So pause, see if you can do these for a second. Okay, hopefully you tried that out. If I look at this first one, right, I see that I make a new CC bond here and that there's an OH. So right away I'm thinking that it's a Grignard reagent because there's an OH at my new CC bond. So I just need to get a halogen on there. It doesn't matter which halogen for the Grignards. So let's say I do the chlorination. So Cl2, AlCl3. Again, it doesn't matter which carbon you put this on. I'll just put it on here. Then I'm going to add my magnesium metal. So that'll make my Grignard reagent, my magnesium chloride. And then I need to add, as step 1, I need to add that aldehyde. Right, looks like I have 1, 2, 3, 4 carbons. So I'll make that aldehyde, step 1. Right, it matches up with these 1, 2, 3, 4 carbons. And then remember with the Grignards, afterwards, there's always some sort of acid workup. I like ammonium chloride, but really just any acid would be fine. So I can use this for a synthesis problem, right? I can use it to like make an aromatic ring, a Grignard reagent. I could also look at this one over here on the right. I'm seeing that I have a new bond here, and there's an alkyne, so I'm thinking Sonogashira right away. That'd be the easiest way to do it. We'll see that there will be other ways, but the easiest way is probably Sonogashira. That's going to take the fewest steps. So I will go ahead and put a halogen on here. Let's say I put on sodium iodide, or you could put on a bromide. So that I slap an iodine on there. And then I'm just going to do a Sonogashira. So I just got one step left. I'm just going to add that terminal alkyne, add some sort of palladium, add a copper 1, and add a some sort of amine. So I'm using DIPA, the diisopropylamine. Could use TEA, could use other things, but Sonogashira gets me there real quick, right? So now we know ways to get halogens on aromatic rings. So it kind of opens up some of those organometallic reactions for us. So watch for the next video. I'm going to do the sulfonations and nitrations in the next video, so that we can add on we can expand how many things we can do to these aromatic compounds. So watch for that. Study up. Good luck.